right, thank you very much, Dr. Cogliano. Now we'll hear all about the adverse outcome pathway from Gary Ankley at US EPA. Will be joining us remotely. Specifically, he'll be talking about his presentation is entitled "The AOP Framework and Causality: Meeting Chemical Risk Assessment Challenges in the 21st Century."
Hi, are my slides up there? The view I have here is a little small.
Yeah, you're good to go.
Okay, great. I'd like to have been there in person today. This is a fascinating meeting, and it's a topic I'm very interested in, but I am glad to have the opportunity to talk a little bit to all of you about the AOP framework in the context of causality. I'm also with the US EPA. I'm with the Office of Research and Development at a lab in northern Minnesota. You can see a picture of the lab here on the shores of Lake Superior. Our more prominent season's on the right here. This lab's been involved in ecotoxicology research now for about 40 years, and so I'm going to be talking a little bit about some of that as I show some examples with AOPs. I've got a few slides just in terms of background. Most of you know all this already, but it's worth repeating, I think, in the context of what I'm going to present. This is a graphic from a few years ago in an article in the Scientific American, a popular science journal, that really lays out the challenges we face as regulatory toxicologists. There's lots more chemicals out there than we have the ability to test, basically. And so this introduces a huge uncertainty relative to chemical safety assessments for both ecological and human health. And as was pointed out in the previous talk, we're not going to test our way out of this using kind of the conventional approaches that we've used for testing in the past. This has been recognized in a number of fora. All of you are familiar, of course, with the NAS report 2007 that laid out the challenges that we face in terms of doing an adequate job of looking at the chemical universe relative to safety. And although these different white papers, reports come from different perspectives, some are human health oriented, some are eco-oriented, at their core they all make the same recommendation. That is, we need to make greater use of predictive approaches to understanding chemical effects in those instances, which is usually the case where we have limited data. The basic approach to doing this, I think, can be captured in the 4 bullets in this slide. First, we need to identify those normal biological pathways that, when perturbed, result in the sorts of things that we consider to be adverse, whether it's changes in reproduction, increases in cancer, etc. We then need to determine those chemical characteristics that enable them to perturb these pathways. Do they interact with enzymes, receptors, membranes, etc.? And then develop what we call mechanism-based approaches, more rapid, cost-effective approaches to measure or predict these characteristics. They could be computational methods such as QSAR models. They could be in vitro assays, including those, as discussed in the prior talk, that are amenable to high-throughput testing, or they could be short-term in vivo tests that you can do in a day or two as opposed to the weeks or months that more conventional testing approaches require. The final point was also alluded to in the previous talk, and that is it's not enough to collect these mechanistic data. We need to be able to translate them in a transparent manner to something that risk assessors and regulators can use with confidence. It's this latter point that a group of scientists at the Duluth lab sought to address with a publication that came out a few years ago now, describing the adverse outcome pathway, or AOP framework. What this is, at its simplest, is basically a depiction of a molecular initiating event. That's the white box on your left. This is the initial interaction of a chemical with a biological macromolecule, the subsequent chain of events that occur across biological levels of organization in response to this, and then the culmination in an adverse outcome defined either at the level of the individual or, as is often the case for ecological assessments, at the population level. So pathway-based approaches to toxicology are nothing new. We're all familiar with mode and mechanism of action, the toxicity pathway concept in the NAS report. But there are some relatively novel attributes relative to the AOP depiction. First of all, it introduces a common, unambiguous terminology in a transparent, formalized structure that really enhances communication not only among scientists but between scientists and risk assessors, which is one of the significant challenges that you face when you're talking about translating mechanistic data. The AOP concept also promotes what we might call a chemically agnostic approach to understanding pathway perturbation. That is, any of a number of chemicals could impact a molecular initiating event, but after this, you're really basing your analysis on response considerations across a pathway. So this enables you to start more effectively treating chemicals based on their biological similarities, key biological similarities, which of course helps analyses related to read across, etc. This final point, and this is obviously the most relevant to this particular workshop, is that the AOP explicitly establishes causal linkages between the endpoints that are depicted, between mechanistic endpoints and the apical outcomes that can be assessed using a weight of evidence approach, and I'm going to talk about this a little later. For these and other reasons, the AOP concept has attracted quite a amount of attention both in the scientific and regulatory communities. One example of this involves activities coordinated through the Office for Economic Cooperation and Development. I know most of you in the audience are familiar with OECD activities related to harmonization of approaches for chemical safety assessment. And so early on, the OECD recognized the potential value of a unifying framework such as the AOP framework and launched an AOP development program in 2012. This program has been focused on a number of activities, including the development of standardized guidance documents for describing and assessing AOPs. So here you have standardized conventions and terminology, information content. The OECD also has supported the development of an AOP knowledge base, which I'll touch on in a second. And importantly to our meeting here, has initiated on a formal approach to reviewing AOPs and AOP knowledge that's based on causality as evaluated using modified Bradford-Hill criteria, which I'm going to be discussing. Again, I briefly wanted to touch on the AOP knowledge base. This is a core that's populated by a number of modules, the most active of which is the AOP Wiki. This is a module that's been developed largely by scientists at the US EPA, as well as the Joint Research Center in the European Commission. And what it is an open source platform for developing AOPs. So you can have multiple research groups, for example, working on a given AOP simultaneously in areas that are best suited to their expertise. You have a standardized input format for this information. And in addition to serving a developmental role, the wiki has an archival role for people that need to use or want to use AOP information. There's currently about 170 AOPs at different stages of development and review in the wiki. They roughly equally represent those applicable to both eco and human health. As I mentioned, another important activity, both here within US EPA and internationally, has been the development of approaches to review the robustness of AOPs and AOP knowledge. This is obviously critical to support implementation. You could have, for example, AOPs at all different levels of development. Those that are more uncertain, less well-defined, we often call putative AOPs, where you have a pretty good idea of the relationship between a molecular initiating event and an adverse outcome, but it may not be quantitative, it may be a little incomplete. So these sorts of things you could envision working on problems relevant to the left of this continuum, where you may be screening or prioritizing chemicals, whereas to do quantitative predictions of risk, you need more robust AOPs that have quantitative knowledge. The challenge, though, is how do you formally assess AOPs using basically causality as criteria? To do this, there's been an emphasis on the Bradford-Hill criteria. Everyone there is familiar with the original publication from Bradford-Hill describing 7 or 9, I forget which, different criteria for evaluating epidemiology studies and causality. These have been later adapted to a number of other uses, including assessing contaminant effects in wildlife. There's an ecoepidemiology publication by Glenn Fox that describes that. And the criteria also been adapted for things like assessing linkages between exposure and effects of endocrine disrupting chemicals in humans and wildlife. More recently, modifications of the criteria have been adapted to the mode of action framework that's been pretty active through the World Health Organization. And then most recently, these have been further adapted for weight of evidence assessments of causal relationships reflected in AOPs. Before I talk about the modifications and the applications of Bradford-Hill criteria, I want to revisit the AOP framework just a little bit, because even over the 6 years since it's been published, there's been, I think, developments in the standardization of the terminology. So this is essentially the same cartoon as I showed earlier, where you have a molecular initiating event, subsequent key events across biological levels of organization, and then adverse outcomes. But in terms of the key events, it's important to note, these are sometimes called nodes, by the way, by modelers, but it's important to note that these are measurable and verifiable. So they're changes in a biological state that can be actually measured and demonstrated. Linking these key events, these nodes, are key event relationships or edges, and these are really the basis for understanding causality using these modified Bradford-Hill criteria, where you can evaluate plausibility of relationships as well as bring to bear empirical support that helps define the robustness of an AOP. In terms of using these modified Bradford-Hill criteria, the three that are essentially brought to bear, and you've probably heard variations on these already at the meeting, perhaps this morning, but the most important is biological plausibility. That is the proposed pathway consistent with established knowledge of essentially normal biology? And this needs to be based on what we call mechanistic relationships and not just correlations. Also, essentiality is another core criterion that is critical to causality. And essentially what you're demonstrating here is that if you can modify an upstream event, for example, stop it from happening, that you see the same response downstream. So essentially you can prevent or reverse these downstream key events by modifying things upstream. There's a number of approaches to do this. We're all familiar with knockout, knockdown models, but you can also do this sort of analysis using what we call perturbation recovery studies. I'll show you an example of that in a little bit. And then finally, there's a number of lines of empirical data that can be brought to bear in terms of establishing causality in AOPs, including evaluation of dose-response relationships among key events and time concordance of responses between upstream and downstream events. Also, you can use empirical evidence relative to consistency of responses across multiple related test systems, for example, species or chemicals that you would predict to act in a similar fashion. Now, to actually demonstrate the application of these criteria to an AOP, I want to use a very simple example. and I apologize to the audience, but this is really more of an eco-oriented example, but really the concepts are the same whether you're worried about ecological or human health effects. And here we're looking at an AOP that features a molecular initiating event of inhibition of cytochrome P450-19, an enzyme called aromatase. We know that there's a number of chemicals in the environment, pesticides and drugs, that can inhibit aromatase activity, and that many of these chemicals also inhibit reproduction, in this case in fish. From this, we proposed a few years ago now a hypothesized or putative AOP that combines the molecular initiating event to this adverse outcome of decreased reproduction. The components of the AOP are shown along the bottom here. Aromatase is critical to the production of steroid hormones, and in females in particular, the production of estradiol by the ovary. Decreased estradiol signaling can reduce the production of this key protein, vitellogenin. This is called egg yolk protein, thereby inhibiting potentially development of eggs and decreasing spawning. So how can we take this AOP and subject it to our weight of evidence causality analysis? This first slide here shows what we know about biological plausibility of the first three key events, the molecular initiating event and these two key events. We know from a fairly rich history of comparative endocrinology that aromatase is the key enzyme controlling the relationship between testosterone and 17-beta estradiol. So basically, if you decrease aromatase activity, there's every expectation that estradiol levels will go down. So this is well established as a normal relationship. So there's good plausibility here. So what happens when we consider some of the further downstream endpoints from the standpoint of plausibility? Again, we know from physiology studies that estradiol regulates the production of synthesis in female egg-laying animals through interactions with the estrogen receptor. This has been shown in a variety of species and a variety of different scenarios. We also know from normal reproductive physiology that vitellogenin is critical to egg yolk formation. It's about 95% of the egg. So obviously, if you decrease vitellogenin, it's entirely plausible you'll decrease egg production, and obviously fecundity is going to affect population levels. So based on what we know about normal biology, this is a very plausible pathway. So what are the empirical data that are out there that would support this in terms of a causal AOP? The first thing I'm going to focus on is dose-response relationships. And this is data from experiments conducted at our lab over the past few years in which a small fish model, fathead minnows, were exposed to fadrazole. This is a drug that's specific for inhibition of CYP19. It was developed to treat breast cancer in humans. So we did a 21-day study with fathead minnows at multiple fadrazole concentrations and then looked at a number of these intermediate key events. If you focus on the box that's just to the left of aromatase inhibition there, or to the right of aromatase inhibition there, you see a significant dose-dependent decrease in plasma estradiol in the fish. This is accompanied by the lower box there, a significant decrease in circulating levels of plasma vitellogenin. So these key events 3 and 4 line up very nicely. If you go to the right, this is a cumulative fecundity plot where you're looking at egg production over time in the fish, and you see this same dose-response relationship. And so across the AOP, you see a consistent dose-response, which lends credibility in terms of causality. The next slide is an example of using temporality or time course information to help establish the veracity of this AOP. In this experiment, the animals were exposed to prochloraz. This is another known inhibitor of CYP19, the molecular initiating event. The animals were collected at different times On the left here, at 6 hours, there's a significant decrease already in the ability of the ovary to produce estradiol. By 12 hours of exposure, you see a significant decrease in plasma E2 levels. And then by 24 hours, this is accompanied by a decrease in circulating vitellogenin. So here you see, in a very nice fashion, this time course relationship where the upstream event precedes the subsequent downstream events in a manner consistent with that depicted by the AOP. Another type of empirical data that can be evaluated in terms of robustness is the criterion of consistency. Here, we know that all fish, all viviparous animals, actually egg-laying animals, essentially utilize vitellogenin, and so and the vitellogenin production is stimulated by estradiol. So basically, any fish species, you should be able to see the same set of responses in. Similarly, we know of a number of chemicals from in vitro studies that certainly inhibit aromatase. So exposure of the animals to these chemicals should produce a similar suite of responses. And here's a subset of the data that are out there examining this. So if you expose fathead minnows, in this case, to fadrazole, perchloraz, or another pesticide called propiconazole, you see the same suite of responses across levels of organization. Letrozole, which is a drug similar to fadrazole, there's studies in Medaka that show you see, again, responses consistent with the AOP, again lending credence or weight of evidence to the robustness of the proposed AOP. The final criterion is that of essentiality. And as I mentioned earlier, this is important, second only to plausibility in terms of establishing causality across this pathway-based approach. And again, what we're looking here is to determine whether or not blocking or reversing a downstream response can be done by inhibiting or allowing recovery of an upstream response. And here you see data from a time course study, an exposure recovery study that we conducted a few years ago with fadrazole. And I can't go into a lot of detail on the design, but essentially the fish were exposed to the fadrazole for 8 days, after which they were removed to clean water and allowed to recover. And we looked at these various endpoints indicated in the red box above, these early key events within the AOP and the relationships of these. So what you see is upon exposing the fish to the fadrazole, you see a very rapid decrease, and this is the left-hand box, a very rapid decrease in the ability of the fish, the ovaries, to produce estradiol. It tends to track back up during the actual exposure. This is actually reflecting a compensatory response in the system. But when the chemical is turned off at day 8, you see a total recovery, in fact, a little bit of an overshoot in the ability of the animals to synthesize the estradiol. If you go to the middle box, you see a very similar pattern, in this case, relative to plasma estradiol levels in the fish. It's a little bit delayed, though, but the point is when it recovers, when synthesis in the gonads recover, you see a recovery in the plasma. And then the box at the far right here is vitellogenin. Again, the time course is a little delayed relative to the other two. It's downstream, but again, you see this recovery by, in this case, day 4 of the chemical-free exposure. So this is an example of establishing essentiality in an AOP. Now, the AOP that I used for my example is one that's received a fair amount of attention, and in fact, it's been through the OECD review process and has been classified as a strong or very robust AOP. And when you can get to this point, you can do some very interesting and important things. And in this instance, one of the things that we're doing is we're developing what's called a quantitative AOP. And here the goal is to be able to use information from the left-hand part of the pathway, specifically the degree of inhibition of aromatase activity, and actually make quantitative predictions as to what's going to happen downstream. The basic approach that we're using to do this consists of using 3 different models that are linked to one another, that inform one another. So there's an HPG axis model that links aromatase inhibition to vitellogenin levels, which then feeds an oocyte growth dynamics model that predicts the amount of eggs the fish will produce, and then this can be plugged into a population dynamics model. Now this is admittedly a lot of work. This is not easy in terms of research, but it does demonstrate how you can use this sort of causality analysis to support this sort of an application for an ALP that potentially could be predictive for full quantitative risk assessment. Now, I blew through that example fairly quickly. I could easily spend a couple hours talking about all the nuances, but I wanted to let you know that there are a number of other resources out there that show how this weight of evidence sort of causality approach can be applied to ALPs. For example, in the Becker et al. Paper in Regulatory Toxicology and Pharmacology, there's a number of examples both for human and ecological endpoints. Different molecular initiating events are listed here, as well as the adverse outcomes in parentheses. In the ALP wiki, there's several other ALPs that have gone through the full review analysis, including the weight of evidence analysis. These are shown here. You can access the wiki and look at these. There's a couple papers that have recently come out of our group looking at this weight of evidence approach to ALPs, one of which I'll point out, it involves actually looking at honeybee colony loss as a consequence of exposure to neonicotinoid pesticides. In this instance, we're using a network of ALPs to make this causal linkage. So to summarize briefly what I've just covered, the ALP framework, we think, provides a tool that's tailored specifically to enhance use of mechanistic data for risk assessment and regulation for both ecotoxicology and human health assessments. Attributes include a standardized terminology, transparent data depiction, and importantly, the incorporation of this weight of evidence-based causality assessment. I'm going to just touch briefly on a couple upcoming activities relative to ALPs. There's a Society of Environmental Toxicology and Chemistry Pelston workshop early next month in Canada that's going to be looking at a number of advanced concepts relative to ALPs, including QALPs, quantitative ALPs, ALP networks, regulatory case studies, and these are both human health and ecologically oriented studies. There's an OECD ALP advisory group coming up in June in Paris that's looking at some of the newer developments, including a new version of the user's manual. I want to conclude by acknowledging the many, many contributors to this sort of work. We have our research team here at the Duluth Lab. I showed some of the data from our group. But the ALP project team in the Office of Research and Development, this is in the Chemical Safety and Sustainability National Project, is actually a fairly large effort. There's about 45 FTE, both from the Eco and Human Health divisions working on different aspects of ALPs. This project is co-led by Dan Villeneuve from up here at Duluth and Charles Wood down in RTP. Also want to acknowledge the people that have been critical of the development of the knowledge base. This includes Clemens Whitweir with the JRC and Stephen Edwards with EPA, who many of you probably know. And then finally, want to acknowledge the input of the OECD Expert Advisory Team. This is a group, this is the meeting in Paris I alluded to. This is a group that's co-chaired by Maurice Whalen from JRC in Italy and Bob Kavlock with the US EPA. So I think that's about all I have. I don't know if I have time for questions or not. I haven't got a clock handy, but I'll see where we're at.